Okay, P4.6, parallel circuits. So you've already seen one parallel circuit, and that was how we hook up the voltmeter to make a voltage reading. Let's do some more. So we've got our power supply, let's say that is 12 volts, and we've got a resistor. So that's your normal series circuit that we were talking about last time. But let's say, however, that we've also got this one. Now it is in parallel, because these lines here are parallel. And an electron going around the circuit, when it gets to here, it's now got a choice. Do I go this way, or do I go this way? Okay, so that's why it's called a parallel circuit, because it does two things at once. It does two things in parallel. Okay. Now, when it comes to the rules about parallel circuits, I like to explain something first. If I cut this wire here, this one is still going to work. And if I cut this wire here, this one is still going to work. So what that tells me is, it tells me I don't have one circuit anymore. I've now got two circuits. So my first circuit is there, and my second circuit, running parallel to the first circuit, is here. And that helps when it comes to the laws about voltage. So we know that this bit here is 12 volts, this bit here is 0 volts. So that means that if we put a voltmeter here and a voltmeter here, well, because they're separate circuits, I can just look at them individually. So I know I'm going from 12 volts of energy per unit charge here to 0 volts of energy per unit charge on this side here. So that means that this voltmeter, V1, is going to equal 12 volts. And I know that the same thing is true for this one, because I know that this one also, the orange one, that has also got 12 volts of energy per unit charge here, and 12 volts of energy per unit charge, and 0 volts per energy per unit charge here. So V2 equals 12 volts. So in a parallel circuit, every branch has access to the light, to the battery, because it's got a separate circuit which gives it its own access to the power supply. So each one's got 12 volts. What that means is that this battery is going to drain twice as fast. Okay, so what effect does that have on the current? Well, if I draw my circuits again, so that's one, that's two, so now, because we said that the electrons have a choice whether they go this way or this way, then that means that the current is going to be split. So if I put an ammeter in here, an ammeter in here, an ammeter in here, and an ammeter in here, you can see that this one is measuring the current of both the orange and the pink line, so that's going to have the total current in the circuit. But this one, it's only got the orange, the current in the orange, and this one's only got the current in the red. And whereas this one, they're back to being together again, the orange and the red. So if I label these up as 1, 2, 3, and 4, I know that the A1 equals A4, because what went in must come out. Okay, so A1 went in, A4 is what's going back out. Okay, those two must be the same, because it's red and orange, red and orange. Now these two will only be the same if these resistors are the same. So if this resistor is a 100 ohm resistor, and this one is a 100 ohm resistor, then A2 will equal A3. But if this one is twice as hard to get through as this one will have half the number of electrons choosing to go around it, because the electrons are lazy. They will always pick the easiest route. So if this one is twice as hard, then twice as many will go this way. Okay? So, and the way that we work that out is, we know that we said that this was 12 volts here, and we know from Ohm's law that V equals IR. So each loop is going to have 12 volts. We've said that. So what if the resistance on this one is 100, times I, and the resistance on the other one is 200 times I, because I've said now that this one is twice as big as this one. Then can you see that if that one is, so if this one is this one here, which is R1, and this one here is R2, then I2 and I1 is going to equal 12 divided by 100, and I2 is going to equal 12 divided by 200, which means that I1 is going to be twice as big as I2. And the way that we work that out is that on every single branch of the circuit, you know that I1 times by R1 is going to equal V on every branch. I2, R2 equals V on every single branch. Okay? And if I want to find out what the total resistance of this circuit was, the way that I do that is I do 1 over R1, add 1 over R2, add 1 over R3, etc. However many you've got, however many branches you've got. But R1 is the resistance of the first branch, R2 is the resistance of the second branch, R3 third branch, R4, and so on. That will equal 1 over R total. And that's how you work out the resistance of a parallel circuit. And the way that I like to think about this is a little thought experiment. So if you imagine that you've got a circuit and you've got a gap in your circuit, and you add a wire across that circuit. Okay, that's now completed your circuit. If you add another wire, have you made it easier or harder for the electrons to get across? Well, obviously you've made it easier because you've given the electrons 2 routes to get across rather than just one. So each time you add a wire, you're making it easier and easier and easier. And each time you add a resistor in parallel, because remember all a wire is a resistor, and all a resistor is a wire where the resistance stays the same. So all of these are just resistors in parallel. That's all they are. So each one is just making it easier and easier and easier. So each one I add on here is making it easier and easier and easier.